Hello class, so this is CSE-5250, Section 2, Week 13. We're almost at the end of the course, so I'm going to take the time to go through a few more examples of parallel programs using NVIDIA CUDA. First I'm gonna look at matrix multiplication, and I'll walk through how that works. And then maybe we can try making one more parallel program together. Not as an assignment, but just something that we can, try to walk through together. Now recall that you also have an assignment where you are recall that you also have an assignment where you're going to look for another use case for parallel programming that we didn't talk about that wasn't discussed in class, and you're going to write a short paper, 1 page, describing that use case for parallel programming. Or if you know of a parallel algorithm that you find interesting, you can describe that too. Also be sure to cite any sources that you have, and this assignment is due, I believe I made it due on the 23rd of November. Yeah, 23rd of November at midnight. Right, so I will also say this right now. The final for the class will be made available sometime during week 15. It's a take-home final that will be due sometime during finals week. So sometime during the last week we can also do a sort of review where we walk through a few questions. That's basically, can you make this algorithm parallel, and if so, how? And maybe I'll throw in a few questions related to Amdahl's law, such as finding the maximum theoretical speedup for a given program with some amount of parallelization. Alright, so let's just get into matrix multiplication. Now, if you've ever struggled with matrix multiplication before, I'm going to illustrate it to the best of my capabilities here. So, first I'm going to draw a pair of matrices. Let's call this matrix A, and it's going to be a 2x2 matrix. So we have A00, A01, 1, A10, and A11. And then we have another matrix here, and let's make it 2 rows and 3 columns. So B00, B01, B02, B10, B11, B12. Okay, so matrix A has 2 rows and 2 columns. Matrix B has 2 rows and 3 columns. Now, when we multiply these matrices together, what we end up getting is, well, another 2x3 matrix. That's because matrix A has these row vectors that are of size 2, and matrix B has these column vectors of size 2. So basically the number of rows of matrix A, the number of columns of matrix A has to match the number of rows of matrix B. I hope this is making sense. But basically, this is how you multiply 2 matrices together. So we get this matrix C, that's the product, and it's going to have entries C01, no, C00, duh. C01, and C02, and then C10, C11, and C12. And since I have these two vectors highlighted, how do we calculate C00? Well, it's simple. It's a dot product. When we take a dot product, we do this. Since I have these two highlighted, so let's calculate it. So C00 equals A00 times B00 plus A01 times B10. So basically, for each row vector of matrix A, we're going to multiply it with each column vector of matrix B. Let me just write this down in words. So for each row of matrix A, we multiply it with each column of matrix B. These are the values these will become the values of each row of matrix C. So if we rewrite this in code, we would have something like, we would basically have a nested for loop. So it would look something like this. Okay, so we have our doubly nested for loop, but it's actually a triply nested for loop because to go through the two vectors requires a third for loop, so we have to iterate through each pair of values, so like that, and that. So really, and typically how this is taught is we have a triply nested for loop, so and then the third for loop is basically iterating for each entry in row and column. So really what you need is a for loop that does this. Okay, it's less than the number of columns of A. So let's just call it A COL. So yeah, the innermost for loop is going to do a dot product calculation, and the other two outer for loops are going to iterate through every row vector of A and then every column vector of B. So let's look at this in code. Okay, so I have a matrix here, and this first function this first function is actually going to print out the matrix, so this is just to make sure the entire thing is working. What we really want to look at is this function here. This is a matrix multiplication function, and it's going to take in two matrices. It's going to find the size of the two matrices. It's going to find the sizes of the two matrices, and it's only going to work if the number of columns of A is the same as the number of rows in B. If that's not the case, in this example, I'm just going to return an empty matrix. The next step is to create an empty matrix that's going to be the size, that's going to have as many rows as A, but as many columns as B. So the product matrix is going to be of that size that I mentioned. Then we enter that triply nested for loop. We're going to iterate through the rows of matrix A, then the columns of matrix B, and for each combination of row and column, we're going to find that dot product and then store that somewhere in matrix C. So we have I and J for our iterators for the rows and columns, and then we have K to iterate through the vectors themselves. So Cij is going to start at 0 because I populated the C matrix to be full of zeros. So we're going to increment it by Aik times Bkj. And that's going to be the entire calculation right there. If we go into the main function, I already had a few examples where I tried it out with a few pre-made matrices. Here is just a for loop. Here's just a pair of for loops where I populate the matrices with different values, but I specify the size, so yeah. And then we have a third matrix that's going to be the product of the two matrices. Product matrix is 2 rows by 4 columns. That's actually from these ones. So really it's going to be X columns by Y columns. For one matrix is going to be X. No. Really it's going to be 2 rows. Yeah. These two matrices that I commented out, they would produce a product that's 2 rows, 4 columns. Here I have matrix A, B, X columns, no, X rows, Z columns. Matrix B is Z rows, 4 columns. If I multiply those two matrices together, I get a matrix that's X rows, Z columns. And if I just run it, I have to enlarge it because there's so much to show. I have our two matrices here, and then I have the product matrix here. So, how do we make this parallel? One way to do this is to use OpenMP. We looked at OpenMP when we were writing the sieve of Eratosthenes in a few different ways. And of course the first one was to use OpenMP. That you may have found that to use OpenMP may be the easiest way of making something parallel, because it's just as simple as looking at the code, recognizing where code can be made parallel, and then just adding a few directives, and that's it. So one way to do it is to add the pragma OMP parallel for on the third for loop. And to make sure that this thing will work properly, not options, I'm going to go to project properties and go to configuration properties C/C++ language, and then I can turn on OpenMP support. And that's it, right? Well, let's take a close look. We have 65, 72.8, and 80.6. And if I run it again, actually what I'm going to do is I'm going to modify the code so that it's going to produce two matrices, but every entry in each matrix is going to be the same values. So let's just push back a 1 in the first matrix and then a 3 in the second matrix. So what do we get? Now, because all the row because all the because all the row and column vectors are going to be the same, we should get the same value, but we're not. And that's because we've accidentally introduced a race condition, and that's because we have multiple threads trying to access the same thing by incrementing it, and we get a synchronization issue that we can resolve by adding pragma OMP critical. And now we get the correct answer. The product matrix is just a matrix full of 36s. That is one way to do it. Another way to do this is to recognize that the dot product calculation is its own for loop, and we just have to iterate through the. We can just iterate. When we iterate through the rows of matrix A, we're gonna iterate through the rows of. We iterate through the rows of matrix B, and then we iterate through the columns of matrix B. What could also work is if we just add the compiler directive on the second for loop. It's going to parallelize the work of this for loop, but not this one. Or rather, it's gonna be done in such a way so that every loop iteration is going to have its own dot product calculation. So to make sure this works, and it works. 1s, 3s, and 36s. Alright, so what I can have you do is play around with this program and have you see for yourself how this works. I have the code available on Canvas after all. But what I also have available on Canvas is a CUDA implementation of the sieve of error. No, not the sieve of Eratosthenes. Well, I actually do have a CUDA sieve. But what I also have is a matrix multiplication program that's programmed using CUDA. So I'm gonna pause the video real quick and I'll continue right from there. Right, so I'm back. So if you were to download the NVIDIA CUDA toolkit that I may have shown a few times already, if you're to start up Visual Studio, you're going to have an option to make an NVIDIA CUDA project. And it's going to populate the entire kernel.cu file with a default program. I've already erased most of that, but really what we need at the least is this: include CUDA runtime.h and include device launch properties.h. If you look here, we have the kernel here that's going to run on the GPU, and I've already coded it, so basically what's going to happen is this. Sorry, excuse me. So what's going to happen is this. You know how we had that triply nested for loop where we had to iterate through the rows of one matrix and then the columns of another matrix? Well, we're going to attempt to do every dot product calculation all at once. And here's how. basically, we're going to divide the work in such a way so that we're going to have the work on this grid of threads. So we have thread idx.x and thread idx.y here. Those are going to correspond to our rows and columns, because each thread is going to have a row and column identifier, you could say. Each thread is effectively going to calculate across all the threads, it's going to calculate every dot product. But it's going to have to do it one step at a time, because it still has to iterate through the pairs of vectors individually. So there are a few catches to this particular example. Mainly, it's going to only work on square matrices. So I guess that's fine for this example. But anyway, yeah, we're gonna have a whole bunch of threads on this grid. And this if statement here is just here to make sure if we have any rows and columns outside the bounds of the matrix, whatever thread is going to try to do that work, it's just not going to. So it's basically only gonna calculate if that thread is somehow within the bounds of the product matrix, if that makes sense. I also have a print matrix function here, similar to the one we had before. Now there is another catch. I had to write the matrices as a one-dimensional array instead of a two-dimensional thing. If you look at the previous example, I coded the matrices so that it's a vector of doubles. That's what this type def means. It's basically a shorthand for me to say, hey, when I say matrix, I really mean a vector of doubles. Instead, I have to have my matrices be a 1D array that's supposed to represent a square matrix of n by n. So it's going to have n squared entries. But that's okay. Sometimes we have to represent matrices that way anyway. Okay, so since these are being declared on the they're being declared on the computer, but then we have to allocate memory on the GPU so that the GPU knows what these things are. So we call CUDA malloc managed. We pass in the address for the three matrices. Matrix A and matrix B are going to be the two matrices we're multiplying together. Oh yeah, as a reminder, matrix multiplication is not commutative. So if you multiply two square matrices A and B in that order, if you swap them so it's B times A, you'll not get the same matrix. You get non-commutative examples like that all the time, such as, hold on. Right, so you get non-commutative operations a lot of the time where the order of operations matter and you can't mix them up. So, for example, if I twist this side into the top, it's going to be different if I did it top and then the side. I mean, look, I don't know if you can see this, but the outcomes are different. Here we have a on one cube I have 3 blue tiles in a row, on the other one it's 3 white tiles in a row. See, non-commutative. Anyway, so we allocate memory on the GPU, and then I'm gonna populate these matrices with values so the kernel has something to work with. Of course, you can just do something else, such as read from a file or do some other way of populating a matrix. But whatever it is, we're gonna have to populate matrix A and B with some values, and then we're gonna populate matrix C with zeros. And then I'm gonna declare these dim trees. It's going to set a specific number of threads for us to work with. The easiest way to do this is if we have this threads per block value be set to n and n. So it's going to work with n by n threads. This blocks per grid, we can just set it to 1 and 1. Because we only need to work with 1 block's worth of threads. And then we can just pass it into the angle brackets here. We call the kernel, we tell it how many blocks per grid, and then we tell it how many threads per blocks. We pass in matrix A, B, and C, and we also have to pass in n, which is, well, the size of the matrix. We call CUDA device synchronize. We print the matrices to see what it's done. We deallocate memory when we're done, and that's basically the end of the program. So let's try to run that. Right. 0.1, 0.2, 0.3, yada yada yada, 0.25, 0.5, 0.751, and so on. Maybe it would help if we just tried a much simpler example. So I'm just gonna set these two matrices to have just one value. One is gonna be full of ones, the other one's gonna be full of threes. So when we do our multiplication operation, it's literally gonna be the same calculation for every entry in the product matrix. So, oops. 1, 1, 1, 1, 1, 1, 1, 3, 3, 3, 3, 3, 3, 3. Multiply 1 and 3 together, and we get a bunch of trees, but then we have to add all the trees, and we get 48. And there we go. Now, I am referencing a tutorial on this. It's linked in the comments, but I also have it linked on Canvas. So basically, let me just get the article. Hold on. Alright, I got the link. It is quantstart.com, and it's an article on how to do matrix multiplication. Now, with this threads per block and blocks per grid thing here, there is a maximum size that we have to keep in mind, and it's 512. So whatever size n is, n squared cannot exceed 512. So there's a max size to this. Yeah. My example here is programmed a little bit differently, but it tries to capture the gist of what's going on. But as a curiosity, 512. The square root of 512 is something like 22.6. So it means there is a maximum size on these matrices. To multiply matrices bigger than that will require a bit more coding, but this is for, I guess we can say this is for matrices smaller than, say, 22 by 22. So I think we're, so I guess I can say we're good on matrix multiplication. If you want to try multiplying even larger matrices, we're gonna have to do some level of rewriting to make this work. But for now, I'm gonna stop talking about matrix multiplication, and then I'm gonna go back to a program that I shared that we can also try to make parallel. So, with that, let me just stop the recording, and I'm gonna pull up the code. So some time ago, early on in the course, I gave a few example programs that we can try to make parallel because they had nested for loops. So this program here is going to find Pythagorean triples. And a Pythagorean triple is a triplet of numbers such that Pythagorean triple is basically an integer solution to... Huh? A Pythagorean triple is an integer solution to a squared plus b squared equals c squared. Simple examples include 3, 4, 5, 5, 12, and 13, and 8, 15, and 17. So basically, if we do this, then the left-hand side and right-hand side will be the same. So it's gonna be a program to find Pythagorean triples. Now, I'll just copy the code, paste it into here, and let's try it. Let's try to run it. Didn't take that long at all. So there are a few solutions that are basically multiples of previous solutions. 3, 4, 5 is basically the smallest Pythagorean triple, but we're seeing it again and again as multiples. So 60, 80, 100 is basically the same 3, 4, 5 triple multiplied by 20. Okay, so let's exit. So let's exit out of that and let's type in a bonkers search max and see what happens. Now, since this is a triply nested for loop and each for loop is basically iterating all the way to search max, it's going to count to 10,000. It's basically counting to 10,000 for every time it's counting to 10,000 for every time it's counting to 10,000. So, what? That's how many possible combinations? Yeah, 10,000 times 10,000 times 10,000 is 10 to the third power. And when I typed it into the calculator, I got a trillion possible combinations to search for. I will say there are way easier ways of producing Pythagorean triples than this. It's just this is a way simpler program to cobble together for the sake of demonstration. And because this is so slow, let's try to make it parallel. And with that, I'm just gonna add in that directive again. So, now, every thread is going to print out something, but it's gonna just print it out as a singular string here. So, it should be okay if I just add in pragma omp parallel 4 and run it again. And let's see if it runs any faster. It's hard to tell whether it is faster, because this is a trillion threads, and no, this is a trillion combinations, and it's operating on 16 threads as per the specs of my computer. So a trillion divided by 16 is what? Each thread is still gonna have to do 63 billion. Each thread is still gonna have to do like nearly 63 billion different combinations of values. So maybe it'd be more productive if we just had it be a search max of 1,000 instead. And I like that it found quite a lot of Pythagorean triples in practically no time. If I did not make it parallel, what happens? want to make sure is, yeah, OpenMP support is turned on. What I can also do is actually what I need to do is include omp.h, and then I can just print out the number of threads I'm working with. Is this working? Okay, maybe I have to see out it instead. Okay. One? Really? That's weird. Do you have to set a thread number? Right. I'm gonna pause the recording again to debug a bit. Okay, did some debugging and it turns out it was working after all. It just may have been a lot of stuff. It may have been a lot of loop iterations to work on, and it would have been slow no matter what. Well, at least it works. Anyway, let's just sit back and watch this thing work. I had it work a little bit already while I was debugging, but anyway. So basically, OpenMP is an easy way of making parallel programs without by changing very little of the code at all. If you're to code using NVIDIA CUDA, it requires quite a bit of rewriting to make it work. On the flip side, once you get it to work, you can get a lot of parallel work done in you can do a lot of parallel work. Basically, what I'm saying is you can get so much parallelization done. So, if for example you had to sift through like a billion different, if you had to do a thing where you had to input a billion different numbers into a function to see which number outputted a specific value, you could have it multi-threaded to an extent where you're processing thousands of numbers at a time. So I guess a challenge for myself that I'd like to show, hopefully by next week, is what it would look like if I had this Pythagorean triples function here parallelized to run on NVIDIA CUDA. No, using NVIDIA CUDA. Because even with 16 threads, this is still pretty slow. Now what I could do is try to throw in more threads to the mix, so if I had it set to 64 threads and I tried to run this thing, the thing is now is this. I remember how my computer has an 8-core 16-thread CPU on it. Yeah, I'm already maxing out my CPU by doing this. And the problem is when you have the context with so many threads, because, well, there are more threads than there are CPU cores on this thing. Technically logical processors, but anyway, that's a challenge that I wanna. That's just one more thing I wanna try to show you for next week before we start looking at example problems for the final. So, oh yeah, one other thing. And this is gonna be more of a mathematics fun fact than anything. I stopped the program just because the Pythagorean theorem is actually a special case of the law of cosines. So if I plug in my tablet back in, so yeah, the Pythagorean theorem is actually a special case of what's known as the law of cosines. Where we have a triangle like this, and side lengths A, B, C, and angle sizes alpha goes here, alpha, beta, and gamma. So yeah, this is the law of cosines, and if we have a 90-degree angle, cosine of 90 degrees is 0, so this entire 2ab cosine c goes away, and then we get the Pythagorean theorem. If it is instead 60 degrees, what we then have is a cosine of 60 degrees, and that is 1/2. So if gamma is 60 degrees, then we have a squared plus b squared minus 2ab equals c squared. And we can play the same game with 120 degrees. If gamma equals 120 degrees, then a squared plus b squared plus 2ab equals c squared. Actually, I got it wrong. It's actually just a. It's just actually ab, not 2ab. So really, this is off by a factor of 2. So let me just erase that, and there we go. So yeah, this is more of a mathematical fun fact than anything. And it basically means, what it basically translates to is the fact that I ended up putting 3 different versions of the Pythagorean triple finder on Canvas, where they correspond to finding integer solutions to each of these 3. And because each one is going to be its own triply nested for loop looking for their own solutions, it's basically just more examples of parallelizable programs. So, as a final example, as I mentioned, I'm going to try to make one more parallel program using CUDA, and it's going to find Pythagorean triples. Right, so I guess that's going to be it for this week. I hope you're working on your short papers that I asked you to write. If you have any questions, let me know. And with that, we'll meet again next week. Next week is going to be a short video on account of it being Thanksgiving. So if I don't have anything for then, on the off chance that I can't get anything, on the off chance that I don't have anything to show for that week, then there will be no video on that week. But week 15, at the very least, I'll have some sample questions for you to work on. Or rather, maybe we can discuss on about what's going to be on the final. Anyway, that's gonna be it for this week. So have a good week. Work on your final assignment. If you have a few things that you have yet to have turned in, turn it in as soon as you can so I can still give it a grade. Right? I guess that's it. See you next week.